So we're almost done, Unit 4, which is the wave nature of light. This topic is electromagnetic radiation, and it's section 10.4 from your textbook. So in the early decades of the 19th century, while Huygens, Young, and others were studying the properties of light, physicists in another sector of the scientific community were exploring electric and magnetic fields. So at the time, light, electricity, and magnetism were all kind of thought separately. Then they started to understand that there was a connection between between electricity and magnetism. And then we're going to get into what the connection is between electricity and magnetism and light. So discoveries by scientists such as Hans Christian Ørsted, André Marie Ampère, and Michael Faraday established the basic relationship between electric and magnetic fields. Other scientists then worked on extending the new electromagnetic radiation theory to related phenomena. So they understood that there was this connection between electric and magnetic fields. And then there was an understanding that there was an electromagnetic radiation. So how electric and magnetic fields sort of radiate. And this was applied to other phenomena. And then what was found was that electromagnetic waves, it were a large spectrum of different types of waves, going from as small as microwaves or gamma rays, rather gamma rays are much smaller than microwaves, to waves such as radio waves, which are quite large, and even the visible light that we see is an electromagnetic wave. So then this understanding of light as an electromagnetic wave then started to give us the answer of how light travels through a medium or through space which is absent of a medium. And the answer is because it's electromagnetic. So we'll get into that shortly, but before we do, I'll mention a bit about Maxwell's equations. These are equations that you will not be using in this course, but you need to understand that just as we have the Newton's equations of motion, which are very important for statics and dynamics, we have Maxwell's equations, which are very important for electromagnetism. So we know that a changing magnetic field produces an electric field, and a changing electric field produces a magnetic field. So how would this help us propagate light or electromagnetic radiation through space, which does not have any particles for a wave to pass through? So let's talk a little bit about Maxwell's equations again. This time I'll refer to the pictures because we've already kind of talked about the first 2 points there. So on that picture you see on the left where we have the different charges. So if we imagine a space, any space that we can enclose, the number of electric field lines that are leaving that space is proportional to the charge that's encompassed by that space. And on the picture on the right, the number of magnetic field lines that enter a closed space is equal to the number of magnetic field lines that leave the space. So basically what we're saying is if we observe a certain space that has electromagnetic radiation passing through it, there will be a certain charge encompassed, and there will be a certain magnetic field intensity encompassed as well, or rather that's entering. So a certain charge would be encompassed, and we can tell what that charge is by what's exiting the field. And the magnetic field, we can interpret the intensity by the fields that are entering that space. So this then gets us, you should be copying down this page. This then gets us to see the image at the bottom that if we have an electric field that's generated, a magnetic field will be generated. So if we have an electric field, a magnetic field will be induced. And if we have a moving magnetic field, an electric field is induced. So we already know this, but what does this mean in terms of how light propagates? Well, if we have every electric field generating a magnetic field, and every magnetic field generate an electric field, then in order for this type of wave to propagate through space, which has no particles for energy to move through, the answer is that the electric field. So the source would be consider the source maybe a vibrating electron at some point. This would create an electromagnetic wave. It would generate an electric field that would radiate out. That electric field would generate a magnetic field. And throughout, every time that magnetic field is generated, it starts to generate the electric field. The electric field then generates the magnetic field, which generates the electric field, which generates the magnetic field, and so on and so forth. This ends up explaining how electromagnetic waves travel through space. Because they are, this is important, they are self-propagating. So that means that, like I said, the electric field generates the magnetic field, and the magnetic field generates the electric field. So they're propagating through space. The medium that they're using is actually themselves. So the medium for the electric wave is the magnetic wave. The medium for the magnetic wave is the electric wave. And the way they propagate, again, because the magnetic force is perpendicular to the electric field, you would see, if you imagine what you see in that image on the right, if you imagine an XYZ plane, epsilon, which is our electric field, would alternate sinusoidally in the y direction, and B, which is our magnetic field, would oscillate in the z-axis, while our wave is propagating in the x-axis. So that image, if you can copy that down, that's an important image to know. Another thing to note, I think this is mentioned a bit later, but I'll mention it now as well, is that in a vacuum, electromagnetic waves travel at the speed of light. So whenever you're given electromagnetic radiation as a question, you can assume, unless it's given told you otherwise, that the velocity at which it's traveling is at c, which is the speed of light, which is a constant that's on your formula sheet. It's 3 times 10 to the power of 8 meters per second. So I'd already mentioned this, but I'll just read through these slides. So it says the changing fields of an electromagnetic wave can be produced by an accelerating electric charge. In practice, this could be from an oscillating current in a coil or from charged particles that change velocity in some other way. In either case, the frequency of the magnetic wave is the same as the frequency of the current producing it. So if we look at the vibrating electron, the frequency at which the electron vibrates will be the frequency of the wave. The 3 central properties of electromagnetic waves are an electromagnetic wave has both an electric field and a magnetic field. The electric and magnetic fields are perpendicular to each other and oscillate in phase. And the direction of wave propagation is perpendicular to both epsilon and B. So I think this slide you should copy down, actually. I thought there was going to be summarized a bit later, but you might want to pause and copy this down as well. So although Maxwell correctly predicted the existence of electromagnetic waves and many other of their properties, such as the speed and ability to reflect, refract, and undergo interference, he never saw any experimental evidence of their existence. It was not until 8 years after Maxwell's death that Heinrich Hertz demonstrated the existence of electromagnetic waves. So here's how Hertz ended up determining this. So what he did was he placed two spherical electrodes close to each other, and then he connected them to the ends of an induction coil. And he would provide short bursts of high voltage. So, as predicted by Maxwell's equations, sparks produced at the transmitter by voltage surges generated electromagnetic waves that travel to the receiver, causing a second spark to flash. So basically, he was able to observe electromagnetic waves traveling from one electrode to another. These waves that he determined were in the radio wave range, and that's what we now know. Radio waves tend to be very large wavelength waves. So we'll talk about the electromagnetic spectrum a little bit later. Actually, I'll mention that rather than mentioning it now. We'll see what that looks like. But it says here, radio waves are usually produced by an alternating current attached to an antenna. As the electrons in the antenna oscillate with time, each oscillation produces a field whose direction is reversed from the first. As such, the frequency of a radio wave generated in this way is equal to the frequency of the current. So another interesting thing about radio waves, if you're trying to figure out, or if you're trying to answer the question of how you tune into a radio station on your car radio tuner, what you're actually doing as you change the tuner, you're changing the oscillation of the electrons in your car's antenna. When the oscillation of the electrons in your car's antenna match the oscillation of the radio waves in the atmosphere, that signal is amplified, and you would then be able to hear clearly what that radio signal is sending. So now the speed of EM waves in a vacuum, this is the speed of light. So as Hertz continued to study the properties of electromagnetic waves, he used the properties of interference and reflection to determine their speed. Hertz set up a standing wave interference pattern using a wave of known frequency emitted from a source and reflected back on itself. So using a receiving antenna, he was then able to detect the location of nodal points in the interference pattern. So then he could find out where these nodal points were, and using that, he was able to determine the wavelength. And then using the wave equation, he set the frequency, he determined the wavelength. So frequency times the wavelength would give him v, which was the speed, and he was able to calculate the speed of electromagnetic waves, and this was very close to what the speed of light was. So at this time, we didn't know that electromagnetic waves were also light waves. But when he found that the V for electromagnetic waves was very close to C, people started to ask the question. His waves that he looked at were at the very low end of the spectrum. They were the low-frequency microwaves with very large wavelengths. But at the time, he didn't know that there were electromagnetic waves, or as the electromagnetic waves increased in frequency, they started to have other effects, including light as one of them. So here you can write this down. Electromagnetic waves travel at the speed of light. They are produced by accelerating electric charges. They consist of interacting magnetic and electric fields that are perpendicular to each other and travel and to the direction of travel, and they oscillate in phase. Electromagnetic waves explain how light can travel through space, or rather how any electromagnetic wave travels through space. It's the changing magnetic field that induces the electric field, and the changing electric field induces a magnetic field. Heinrich Hertz confirmed them experimentally, and he also determined what their speed was experimentally as well. So here's the electromagnetic spectrum. So all electromagnetic waves travel through a vacuum at the speed of light. C is the letter we use to designate the speed of light. It's 2.99792458 times 10 to the 8 meters per second. This is often rounded to 3.00 times 10 to the 8 meters per second. These measurements are so accurate that as of 1983, the speed of light is now used to define the length of the meter. So we can copy this down here, and if you could as well, try to copy that image on the right. If you could also break up the visible light spectrum as well. I would use words rather than colors to do that. And just generally, you would, just in general, having an idea that 700 is red, 600 is yellow-orange, 500 is blue-green, 400 is violet. So another thing to note is, as the wavelength increases, the frequency decreases. And as the frequency increases, the wavelength decreases. So our gamma waves are the very high frequency waves, very small wavelength, and the radio waves have a very long wavelength, but a very low frequency. So here's a question. It says, when television correspondents are interviewed live in a distant part of the world, there's a delay before hearing their responses. So here's a reason why that could be the case. Even though the electromagnetic wave travels at the speed of light, it still will take time for the light to travel from a location in the world to a transmitter, and then back down to an antenna, and then back down to a receiver. So that time distance, even though it's traveling at the speed of light, there is still a noticeable time difference for us, even though it is maybe less than a second. This question here says, microwaves with a wavelength of 1.5 centimeters carry television signals using a sequence of relay towers, and we're asked to determine the frequency. So if we know the frequency, we'll have to use the universal wave equation with C as our V. So C is 3.00 times 10 to the power of 8. This divided by 0.015, that many meters, 1.5 centimeters, will give us our frequency, which is 2 times 10 to the power of 10 hertz. Now it says, how much time does it take for a microwave signal to travel across Canada from St. John's to Victoria? And that is 5,000 kilometers. So this is simply C would equal D over T. So T would equal the distance, 5,000 kilometers, divided by 3 times 10 to the 8. That gets us to 0.016 repeated, or 0.017 seconds. So even traveling across Canada, that's 17 milliseconds. So it's not a lot, but it could be it could provide a little bit of a delay. This next question says, how do microwaves cook food? So this might, if you think about what I was saying earlier about the tuner on your car, on how you pick up signals for a radio, it's the same basic idea. So when we have our antenna on our car, the electrons oscillating at the same frequency as the radio signal, we amplify the signal, and that provides energy. For a microwave, what we're essentially trying to do is we're trying to, or rather, we have microwaves that provide a frequency that is very close to the natural frequency of water, which means that if we bombard food, which our food is contains a lot of water, mostly. All foods have water in them. If we vibrate these water molecules, they will create energy. That energy will then heat up the food. So this is basically the idea. We vibrate the water molecules by sending a signal, a microwave signal, that's close to the natural frequency of water. The signal and the water molecules then vibrate, and that vibration of the water is amplified by the microwave. That vibration provides energy, which then cooks the food. This might be why foods that have a lot more water in them tend to cook faster than foods that are a bit drier. And what you'll notice is often in food you'll see hot spots when you use a microwave. Those are caused by areas that have because it's not because we're not exactly vibrating at the frequency of water. Those hot spots are created because there is a little bit of an offset. There's a phase difference between the microwave and the vibration of water. And for some foods, this will cause vibration in some places and no vibration in others, which will then cause these hot spots to occur, the spots that are much hotter, and cold spots, which are not as hot. Next it says, describe the process that allows an electromagnetic wave to exist as it radiates away from the source that created it. So the wave is self-propagating. Every changing electric field generates a changing magnetic field perpendicular to itself, and every changing magnetic field generates a changing electric field perpendicular to itself. So this is how waves propagate through space. So next, talking about reflection and absorption of electromagnetic waves. So light is the electromagnetic wave lots of us are familiar with, and you see light reflecting off a mirror. Now you've probably seen satellite dishes around. You might be wondering why those satellite dishes are gray, and they're not exactly as smooth as a mirror. Well, satellite dishes are actually reflecting satellite waves, which are radio waves. And those radio waves are have a much larger wavelength than light. So in order for a radio wave to reflect, the surface doesn't need to be nearly as smooth as it does for light to reflect, like a mirror, like the smoothness of a mirror that you see. So a gray satellite dish reflects just as well as a highly reflective mirror satellite dish would. And you probably do know this, but the satellite dish has a parabolic shape with the focus of the parabola at the receiver. So it's essentially taking any radio signal that hits that satellite dish and sending it to the one point, the focus, which is then sent to the television or whatever else is receiving that satellite signal. So here we're going to look a little bit more at how that happens. With light, the atoms need to be tightly packed together in order for there to be a reflection. Because if the atoms were not as tightly packed together, the light would slip through because of the very small wavelength of light. With so it says here, basically, at the last sentence says, theoretically, if atoms were larger than the wavelength of light, it would be impossible to make a mirror that acted as a good reflector. So if the atoms were larger than the wavelength of light, we would never be able to have the light bounce off the atoms. The image that we don't have here would be if we have a satellite wave, which is a radio wave, it would be much larger. The distance between the atoms doesn't need to be nearly as close as it does in order for us to have a reflection. And I'll let you read that a bit more, just so that you fully understand that. So if you'd like, please copy this down. You might want to pause. So the amount of energy reflected depends on the wavelength of the incident wave and the material it is striking. In general, the shorter the wavelength, the smoother the reflecting surface must be. This question says, would a mirror designed to reflect longer wavelength infrared radiation need to be smoother than a mirror designed to reflect shorter wavelength ultraviolet radiation? The answer here is no, because the longer the wavelength, the less smooth the reflecting surface must be. So if we have a mirror that's already designed to reflect long wavelength light, it would not, it would need to be smoother. Oh wait, no, sorry, I'm reading the question wrong. Let me read this again. It says, would a mirror designed to reflect longer wavelength infrared radiation need to be smoother? It would not need to be smoother. It could be less smooth than the mirror that's designed to reflect ultraviolet radiation, because the mirror designed to reflect ultraviolet radiation would have to be very smooth relative to the longer wavelength mirror. Another question here, it says microwave oven doors have metallic screens embedded in them. Light passes through those screens, but the microwaves do not. So let's assume that the microwave radiation is on the order of 10 to the power of 10 hertz, and the light is on the order of 10 to the power of 14. So calculate the wavelength of both the microwave radiation and the visible radiation. And the answers are there. I won't calculate that because this is relatively simple. Now, the wavelength of the light is very small, 3 times 10 to the negative 6. The wavelength of the microwave is 3 centimeters. So why would a metallic screen with those big holes be used? Well, those holes themselves are large enough to allow light to pass through, but small enough to block the microwaves. Because the microwaves themselves are 3 centimeters, the microwaves would hit those holes. They would not pass through. They would not pass through the screen at all. And remember, the frequency of them would result in them hitting, even if they pass through the hole at a certain point, they'll hit inside the thickness of the hole. So with that, we'll stop this lecture. There's a lot to understand here, so if you need help, please read your textbook as well. You can also ask me questions on the course website.